Hi guys, welcome to this video. This video is going to be using the A2A Simulations 182 Cessna Skylane, which is a marvellous rendition of the 182. And we're going to be using it specifically because of its high fidelity so that I can demonstrate and talk through the constant speed prop or the constant speed unit. Now, a couple of things really. This video is not intended for people who are studying for this thing in real life. It's simplified. If I were to talk about the topic in the level of depth needed for somebody who flies this thing for real, we would be running into hours and hours and hours. These things are quite complex bits of machinery. Actually, the easiest way to learn about them is to see them, poke them, prod them, and see what they're all about. But unfortunately, in the flight simulation world, we haven't got virtual fingers with which we can prod it, and we haven't got a virtual engine on a virtual test bench to prod. However, we're going to do the best we can. So the first half of the video is going to be based around what actually happens in terms of the innards and the propeller and why we might want to do it. The second half of the video is going to be basically focusing on how to use it and answering the question of why is this here? What does this do? This blue knob here. I suspect I fell into the same trap as a lot of flight simulator enthusiasts in the early days. There's three controls for the engine, and they basically go, the red one goes fully in, the blue one goes fully in, and then the only one I know about is the throttle, which is the go faster, go slower, go louder, go quieter button. And fundamentally, the only thing I really used to know is pull it out to stop, push it in and you get your fuel air mixture, pull it out to go slower, push it in to go faster. And the blue one was the mysterious one that sat in the middle like the unwanted brethren. So what we're going to do is, as I say, the first half is going to be a look at what an actual constant speed unit is and how it works. The second half is going to be how to use it in the air. So with that in mind, I shall see you shortly. So welcome to the simplified technical bit, if there can ever be such a thing. But basically, welcome to my design studios. You can see, obviously, I'm an apprentice from a technical drawing design studio, so I do apologise if the standards blow your minds away. But nonetheless, we're going to have a quick look at, I suppose, why we would have a constant speed prop. So over in the right, to those of you who've done any aerodynamics will recognise the shape of a wing here, which is basically all a propeller is. It's a propeller. It's a wing turned on its side, bolted to a few others, and spun at a very high RPM. Now what that then means is it has to produce thrust. It wants to produce thrust in this direction. As a byproduct, it gets drag. So you'll have drag in that direction, and it wants to produce thrust, which is akin to lift, okay, on a wing. So here's our wing. It's turning, rotation is down the screen, so therefore the airflow in effect is up the screen. So if you consider that we're sat on the end of this looking at it, you'd see an effective airflow going up the wing. But because we're moving forwards, we've also got this horizontal component here, and when you add the two together, you end up with this big long blue line with the three arrows. The chord line is the line that goes straight through the leading edge and trailing edge of the wing stroke propeller. And the difference between the blue line with the three arrows, which is your relative airflow, and the chord line is this little green arc here, which is called the angle of attack. And the angle of attack, combined with the speed of rotation, are the two things that vary your thrust. So let's just do a red thing. So thrust is dependent on alpha and speed of rotation, which is RPM. So you're looking at alpha and RPM. Now let's go over to our poor little let's go over here first of all and identify these very complex looking shapes. The first one is this one, which is the engine. This is the hub, and these are the blades. Okay, so these are our main key component parts, and then when you've got we'll ignore one part out of convenience. I'm not going to do anything with it at the moment, but we'll ignore this part down here, which is the little lever that is in the cockpit of most aircraft. The little lever that's red handled, which is the mixture. For the purpose of this, we're going to ignore it. Basically, all it does, it allows you to manually change the fuel-air ratio going into the engine, which is twofold. You can use it for two things. You can choose it to control the performance of the engine in terms of its fuel air ratio and its efficiency, its fuel efficiency. It does have an impact on power as well, but one of the key controls is that it controls the fuel efficiency, with it a bit the power, but also the other thing it controls is the temperature of the engine. It's quite a critical control for that, because if you get your mixture wrong, you can overheat, cause detonation and all sorts of problems. However, we're going to ignore that for the moment. The other control we're all familiar with from the Cessna 172, 152, the PA28, well, some PA28s, not all, is the Let's Rock lever, also known as the throttle. So here we go. It looks like a real life drawing here to me. So throttle. So in a simple fixed pitch, okay, how do we change the thrust? We've said the thrust changes based on the angle of attack or RPM. With a simple fixed pitch prop, we're not going to change the angle of attack, so the only thing we can change is the RPM. So increase the throttle, you increase fuel and air going in, which means you increase the RPM and thus the power. However, the more astute will have noticed that as we go faster, this bottom line changes, which means the whole angle of this changes, which means the green. So let's have a quick look at this. Let's draw it in yellow. Let's assume we go faster. Our line extends out here. This is now our new airspeed. And as a result, our relative airflow is now at this angle. And you can see that the angle of attack is now much lower. So what then happens basically is with a simple fixed pitch prop, what you find is there is one speed at which the prop develops the most power. Any other speed it does not develop as much power, as much thrust, if that makes sense. And the only control you have over how much thrust you develop is just to change the RPM of the engine as a whole. Now there's all sorts of technical issues and problems and variables with that, but fundamentally we're not going to worry about that, because what we're doing is we're going into the advanced 21st century technology of having a pitch that can change. I say that in jest, by the way. They did have variable pitch and constant speed props a long time ago. By the way, there's a difference potentially depending on your definitions between variable pitch and constant speed. Variable pitch is quite often used as both terms, but variable pitch is a propeller where the pitch can be changed, and sometimes it's changed by means of a lever, a manual lever. So the Grob 109, for example, you can change a manual lever and it will go from fine to coarse pitch. Brings me on to another point. What is fine pitch? What is coarse pitch? Okay, so pitch. Fine pitch is where you have a small angle. Coarse pitch is where you have a big angle. Now you've got to remember as well, when you're in coarse pitch, you have increased drag. And when you're in fine pitch, you have reduced drag. Okay. So where are we at? Well, where we're at with the simple thing is the simple engine. We've got an engine, a hub, of blades. They're all fixed. Increase the throttle, everything gets louder, slightly more thrust, and off we go. So increase RPM, you need to increase throttle, which increases fuel air, which increases the RPM, and then power. However, what we've noticed, we've got a problem, is that the fixed pitch prop is only really efficient at delivering that power at one airspeed. Now, one of the things you'll find is that with a fixed pitch aircraft that are STOL generally have a different sort of prop to those which maybe go cruising and touring or operate off runways, because you will find that props often come, fixed pitch props often come with two phrases attached to them. One is climb and one is cruise. Now a climb prop tends to be quite fine pitch, so that at slow speeds you don't have the problem of basically stalling your propeller or having insufficient. So basically what it is a very fine pitch prop, small angle, so that you get best power when you're looking to climb out. So a STOL aircraft will tend to have a climb pitch, a climb prop. The other one is the cruise prop, which is the aircraft that's got oodles of long, lovely tarmac to take off from, but tends to go big distances and wants the best efficiency at high airspeed, you'll tend to find that they have a bigger pitch angle on their blades. So this is all very well and good. We've identified what a single pitch prop is, a simple single fixed engine pitched prop pitched fixed single, yeah. But anyway, we've identified what a 172 is like. So the next thing now is, well, why have they got this big whacking, great big prop element on the front of my 182? And as I say, this is a very simplified thing. This is aimed for flight sim. This is not aimed for commercial pilots or people doing their multi-engine ratings or any of that nature. What we do have is we have another lever. We call it the prop lever quite commonly. However, more correctly, it's an RPM lever. And it sets the RPM of the prop stroke engine, because the two are joined. Now basically what happens is that you have a single RPM for the whole lot, and we'll look at that in the aircraft. I've actually drawn it slightly incorrectly, because we've got another box. It doesn't go straight to the engine, it goes straight to a different thing. So let's draw a box. We'll draw it blue as well, and let's draw it here. And now we can draw a line. In fact, I want a line from there to there. So what's the governor? Because that is what it is, and I'm not talking about an East End London crime boss. That's the governor. Now the governor, what does it do? It controls the RPM. And what's in here is a set of flyweights with an adjuster. So you've got a set of flyweights, and it's geared to the engine. So here's my vague attempt at gearing. And what happens is, if the engine, and by default the prop that's linked to it, goes faster, these flyweights fly out, and there's a spring mechanism, and as they do, it recognises that the flyweights have moved, that they've changed position, and therefore the governor recognises that the engine has oversped. It's gone faster than was demanded. Now I'm going to choose green here. What then happens is the governor has an oil line that goes into the hub, and the governor changes the pressure of that oil line, and the oil line acts on a big piston. So you've got a piston in here, and the piston then changes the pitch. So you've got piston changes the pitch. So let's have a look at, we've set our speed, let's have a look at overspeed. Okay, so overspeed. The engine is going too fast. So what happens is the governor changes the oil pressure, which changes the position of piston, which then changes the angle of the blades, makes them coarse, and as we've seen, one of the byproducts is drag, so the coarse blades increase drag and slow the engine down again. Okay, so that's where we're at. So we've got our propeller RPM lever. Let's assume we set it to 2400 RPM, and this and the governor are now maintaining the engine at 2400 RPM. We want to go faster. So if we want to go faster, or produce more thrust, I should correctly say, what do? Well, we'll choose a new colour. To go faster, we're going to increase the throttle. Okay, that's the first thing. That increases the fuel and air going in. Now that's going to tend to want to increase the rate of the speed. So basically what happens is you get a momentary increase in RPM. However, that's then detected by the governor, and the governor goes, we don't want to change this RPM. I've been set by this, so don't want to change my RPM. So what I'm going to do is I'm going to change the oil pressure. And that oil pressure changes the angle on the blades. And that angle on the blades, if you're increasing throttle, makes them go coarse. makes them take bigger bites of the air. And because it takes bigger bites of the air, it has more drag, which slows it down again. So that's how it maintains the speed. But obviously what happens is you end up with more thrust because you've got your bigger bites of air. So there we go. In summary then, what we end up with is we set our propeller RPM lever to tell the engine what speed we want it and the prop to turn at. If we'll do it the other way. We'll decrease the throttle. So we'll reduce the throttle. So we have less fuel and air going in. The tendency is going to be for the RPM to want to drop because the engine is now producing less power. The governor goes, hang on a minute, you can't drop because we've set our speed. So what we'll do is we'll change the oil pressure going into the piston in the hub. That will allow the piston to move, which will then allow the blades to move into a fine position or a finer position. Smaller angle of attack means there's less drag on the blade. Less drag means the engine then doesn't have to work as hard. And because it doesn't have to work as hard, it doesn't slow down. However, consequently, we also have less thrust being produced by the engine. There we go. Absolutely clear as mud. Let's jump into the aircraft and have a look at this in operation. And welcome to this bit of the video now. So we've seen how it works in theory. We've seen how what the aim and intent of it is. So what we're going to do now is we're going to have a look at actually how it works. Now this is the bad boy here. It's 3-bladed prop. As I said before, I'm using the A2A Simulations 182 because it's such a good rendition of the aircraft that actually I can be confident that when I mess around with stuff in the cockpit, that actually what I'm getting as feedback from the engine, the dials and the aircraft performance is pretty much bang on. So there we go. Now one of the things that people have mentioned previously is why I've done videos where I don't bother using the checklists. My videos predominantly are not designed with a view to or intended with a view to replicating the checklists. They generally have certain specific objectives in them. So whether it be looking at the engine, whether it's looking at the handling, or even just a general review of an aircraft. However, one of the guys on the A2A Simulations website did actually say, well, you know, is there any chance that you could use the checklist properly so that people could see the full use of the checklist and the integration with the aircraft? So I'm quite happy to do that, and we're going to do that today. But the other thing is it actually fits in really well with what we're talking about, because constant speed props are difficult to master if you don't really take in a lot of the basics. So you can see up here we've got our power settings reminder. Pilot's notes, it's a reminder. It's not necessarily the full manual, and in fact it isn't. When you look at A2A's documentation particularly, Real Air do a similar sort of thing. There's a lot of information in those documents that really, if you can take in that information and operate the aircraft accordingly, you get so much more out of it. But we've got power settings reminder, climb 2400 RPM, 23 inches, manifold pressure, 15 gallons per hour, 80 to 95. So the first thing at this point is we're going to have to look at the panel and go, well, hang on a minute, there's some new gauges here that we're not used to. So we've figured out the nice blue lever because that's nicely coloured. We know our RPM dial and our gauge because that's in most aircraft. Certainly most piston aircraft will have RPM directly. And in a 172 or a fixed pitch prop, we know that this correlates pretty exactly to what the throttle's doing all the time. Now, over here we've got a new gauge. We've got the manifold pressure gauge, and the manifold pressure is quite simply the pressure or the air pressure of the engine, of the air that's going into the engine. And quite simply, the higher the air pressure, the more air is getting into the engine. The lower the manifold pressure, the less air is getting into the engine. Now the air takes with it fuel, and so that mass of air and fuel is in effect how much power you're asking the engine to develop. And that's controlled by this bit. So that actually, unlike a fixed pitch prop where this is always controlled by the throttle, in reality now with a constant speed prop, the throttle controls the manifold pressure and the prop RPM lever controls this half of it. Now there is an interrelation, and I'll explain that in a moment. But you can see we've got the rough idea of the settings. If you go into the actual settings in the manual, you'll see more, and it's quite easy to get hold of settings for all sorts of aircraft and all sorts of different setups. But as you can see, when we go through this set of checklists, there's enough detail in here for us to be getting on with. For example, in the climb, it dictates what we should be using in the climb. The interesting one is when we get to the cruise, it says 15 to 23 inches of power, which is anywhere in the green band, combined with 2,000 to 2,400 RPM, which is anywhere in the green band. Now that's a huge scope, and it's important, I think, that we actually discuss that once we're in the air. So without further ado, let's get ourselves into the air. We are going to run through the checklist, as I say, to give A2A's aircraft the credibility it deserves for the finesse of its simulations, and also it gives us a backbone, if you like, for what we're going to do. So aircraft weight and balance is checked, parking brake is set, control wheel lock is removed, look, it's down here, ignition and avionics are all off, master switch is going on. What we're going to do then is check that the fuel quantity is sufficient, static pressure air source valve is off. What I will do is I'll plug in my headset as well whilst I'm here, because the engine gets quite loud. Annunciator panel switch test, so you just hold that, flick it up, all the lights should come on and flash, and then when you let go, only the ones you're expecting should remain on, so they flash for a bit. Pitch trim will go out, says he with confidence, and you're left with the oil pressure, the left and right vacuums. The vacuum pumps, by the way, produce the vacuum, the suction, which is what you then use. There is vacuum, look, suction, which is then what's then used for the gyros for things like the AI. So gyro stabilized instrument like the AI. The difference is that this is a gyro stabilized instrument, the turn coordinator, but you'll notice it says DC electrical, so there's redundancy that if you lose your gyros, you might lose this, but you won't lose this as well. If you lose your electric, you'll lose this, but you won't lose your gyros as well, which is why they're air. So there's a certain element of redundancy for instrument flying, which is very nice. We like that. That keeps us safe and happy. But without further ado, we're draining the battery, so let's get on with this. The annunciator panel we've done, so fuel selector valve is to both. Cowl flaps are open. Flaps we need to extend, so let's put those bad boys down. Good practice to watch them extend, to make sure they come down evenly, that they don't drop and there's no stutters in them. It does take a while to motor. You'll notice while it's motoring as well, we get a volts warning light to tell us that we're using battery power. And then as soon as they're down, master switch off, elevator trim set for takeoff, which it is. And then we go on to page 3. Engine starting. So what we're going to do is we're going to check full and free movement of the controls first. So full and free movement of the throttle, we'll crack that. We'll check full and free movement of the prop and check full and free movement of the mixture, and we'll leave that lean for the moment. Now, before we turn the batteries on, the next thing is I notice a lot of people, as soon as they jump in an aircraft, they automatically put the nav lights on, then they put the beacons on and put all the things in. Generally speaking, in general aviation, you try and keep the load on the battery before starting as low as you can. So a lot of the time what happens is you'll put the beacon on to indicate that you are either about to start the engine or on the engine is running, but you generally leave most of the other stuff off as long as you can. So I know in an airliner the general consensus is that basically what happens is whilst the nav lights are on, there's crew in the aircraft, and the aircraft is in effect in operation, for want of a better way of putting it. And then as you're about to start the engine, or whilst the engines are running, you have the beacons on. And then consequently, as you get to your line-up position, you'll put your strobe on, and at any point between the two, you will either have taxi or landing lights on, depending on your manoeuvres. But for general aviation, the only light we generally start with is the beacon, and mainly because it's got quite a low drain on the battery, but it's inadequate to warn people what's going on. So we've cracked the throttle, the mixture's fully out, the prop control's fully in, master switch is going on, beacon goes on, cowl flaps are checked open. The next bit we're going to do is we're going to put the fuel pump on, and then I need to get my 17 hands together for this. Fuel pump on, put that in, out, fuel pump off, check the area's clear, blah 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 blah, it's clear, shout clear prop out the window, do all that good stuff. And then what we're going to do is we're going to try and get it started, and hopefully it will start. And there we go. Now the aircraft has been flown fairly recently, so as a result of that you can see that the oil T's and P's come up nice and quickly. We're expecting the oil pressure within 30 seconds. And in addition to that, now what we need to do is check the voltage, and you'll see that we've got a voltage light here, and where's it gone? Lost it. Amps, sorry, here we go. Right, I'll explain this a little bit. When it's below the 0, it means there's a drain. You can see minus 3.5 amps. There's a drain on the battery. So the battery at the moment is what's powering the electrics. When we turn the alternator on, alternator on, you should see it go positive, which means it's charging the battery. So all is well there, and our volts light should be out, which it is. Okay, so that's all good. Navigation lights on as required. My eyes aren't good enough for this. There we go. So they're on, and then finally avionics are going on. So hopefully I've turned everything off. The GPS is on, but that's not a problem. So let's turn everything on. We'll just flick it all on. I'm not particularly overly concerned about the avionics being used. And then flaps retract. Now the good tip of the day is when you retract your flaps, do so in stages so that you can see it stops at each stage and that you can see you've got simultaneous even retraction. Same both sides. You can just see it under the wing, under the door there. Now, I haven't got easy dock set up in this aircraft, so you'll have to accept my apologies for the fact that we look round like some sort of golden retriever on steroids looking for its toy. Okay, before takeoff. Now, fortunately, the oil T's and P's are all in the green, so what we'll do is we'll just go and do a run up. So, seatbelts, doors, etc. are all fine at the moment. We will close that. We'll go up to a run-up area. This is at Coventry, by the way. It's FTX Global. So although I do have FTX England, it's not currently installed because I'm moving everything over to Steam. The reason I'm moving over to Steam is because it gives me an opportunity to do multiplayer and shared cockpit more readily than FSX Legacy. And I initially poo-pooed the idea of doing that, but fundamentally I've got a colleague who wants to do some shared cockpit stuff, and the fact that FSX allows you to do that is one of the main attractions to it now. So it also happens to run a bit more stably on my system. So we'd normally do this in a run-up area. So before takeoff, seats, belts and doors are all checked secure. Flight controls, full and free movement in the correct orientation, which they are. I like the fact that as you mess with the elevator, look, you can see the nose bobbles up and down. Fuel quantities checked is full, mixture rich, cowl flaps are open. Fuel selector is both. Throttle, we're going to go to 1800 RPM and do our engine check. If you get any bounce on the needle, by the way, like we're getting there, the chances are it's a bit of a fouled plug. So we'll see what happens. Mag check now, we'll go 2 to the left, 2 to the left, which gives us a drop of about 100, stabilizes and restores, and then 1 to the left, again a drop of about 75 there, a bit of a wobble, and then restores, not too much. Prop control cycle, pull it out, you'll hear the noise of the prop change as it bites the air, and then you'll see it settle at a lower RPM. Put it in, it should restore to its 1800 again. Pull it out again, see it settle, and then push it in again. Pull it out again, and push it in. We will lean whilst we're here in a minute. So everything over here is correct in terms of instruments, no annunciations. Bring the throttle back to idle, waiting for it to idle about 700 RPM, something like that. And it comes down and it does idle. It could be argued, why would we do an idle check? Let's just lean off while we're here, hopefully without stopping the engine. Couple of things. Why would we check that the engine idles adequately? Well, we would check the engine idles adequately because the last thing you want is, if you're on an approach, to find that the engine doesn't idle and that instead actually what it does is it tries to run at 1200 RPM all the time, because then what happens is you struggle because you've always got an engine producing power. So that's the first thing there. The next thing to consider is why we cycle the prop. Well, inside here is basically a piston that moves backwards and forwards, and as it moves backwards and forwards, its control linkages adjust the pitch on the blades, the angle on the blades. Now, in order for that angle to change, you have to be comfortable the piston moves. Now, there's a couple of things. The first thing is that if the mechanism is broken, then obviously what's going to happen is you're not going to get the required pitch changes in the propeller blades that you want, which is a bad thing. The second thing is, even if it did work, the last thing you want is to have oil that's sat in here, because it uses engine oil, by the way. The last thing you want is engine oil that's been sat in here for 2-3 weeks, not moved, not been cycled, because it's stale, it's thick, it's horrible. And if you have to make engine power changes fairly quickly during a takeoff for whatever reason, or it doesn't respond, then you're going to know about it, and that's a bad day. So that's why you cycle the prop, is mainly to get clean oil into this, warm, clean oil into it, and also to make sure the system works. So there you go. That's why we do that. So we'll go straight to landing lights, because there's nobody else around here to affect, and the threshold's over here, look, and we'll go and get ourselves airborne. So, done all that lot. For takeoff checks, wing flaps set, we're having no flaps, got a nice long runway. Power's going to go to full 2400 RPM. What we need to do is make sure that the mixture is fully rich, because we've just had it leaned off. Easy to forget that. And then we'll take off, climb, and then we'll go and have a bit of a mess around, so to speak. In a professional sense, of course, nothing but a professional sense. Okay, now, before we go onto the runway, the next thing I'm going to point out is the behaviour of the dials. So here we are, we're just shy of the runway. What I want you to pay attention to now is the fact that this down here, the RPM gauge, the tachometer, which is basically engine RPM, on the ground, despite what we do with this, that acts exactly like a simple, straightforward fixed pitch engine does. Now, because we've got a manifold pressure gauge, that changes as well, and you can see it moving as I gently move the throttles backwards and forwards. I will lean us off a little bit so we don't foul everything before we take off, but not that much. Just pop it back in. Maybe we leaned off a little bit too much there, but hopefully we'll stop the plugs from fouling. So basically what you then have is a very similar situation to having a fixed pitch prop. Now the reason is that this governor has been set for 2400 RPM. Up here, look where the red line is. Up until the point where the engine is at 2400 RPM, there's nothing the governor can do. The governor can't artificially speed up the engine. The engine has to be capable of producing 2400 RPM. Now at the moment we're idling at about 1200 RPM. We've got it set 1200 RPM. It doesn't matter what the prop does, it cannot speed the engine up. So when the engine power is set to a low setting, either because you're taxiing on the ground or because you've got a really low power setting in the air, this then becomes directly linked to your throttle settings. However, once you are above the speed where the governor becomes operational, this will stick to whatever setting you've put the governor at. So basically this is your governor speed control. Okay, so what we'll do is we'll get airborne, we'll take the brakes off. We shouldn't need much more than this to brake away and get some power on. Nice squeak from the brakes as they've just come off there. As I say, got to remember that we go back to mixture fully rich, get as much power out of this engine as we can. It's 1800 hours old. I've chosen to use an old aircraft. If you go into one of the menus, it allows you to. There's a little button that says used, so you can choose to have your aircraft used as opposed to pristine factory conditions. So this one's got about just under 5,000 hours on it, something like that. I think it is. So we'll line up and we'll just go straight for it. We're not going to mess around. Okay, so this thing rotates between 60-65 knots. We expect it to lift off the ground probably about 65 to 70, and we're going to climb out. We'll aim for a climb of 85. Airspeed's indicating. Runway's indicating my poor rudder controls. 50 knots. 60. Start a gentle pullback, and there we go, we're airborne. Bit of right boot just to try and control the nose a little bit, keep the wings level. With 70 knots, nose forwards a little bit just to gain some speed. Now this is not the point to start messing around with your RPM, with your prop controls. You're very close to the ground, and this is one of the things airliners you'll notice in real life only start to mess around with putting autopilots on at about 400 feet. The reason for that is if there's some sort of failure then ultimately what happens is you've got your head down in the cockpit whilst the plane is in a very dangerous and precarious position, and that is the last possible thing you want to be doing. However, at the moment we're climbing out, we're quite nice and stable, we're at just under 85 knots, fairly well trimmed, not perfectly trimmed by any stretch of the imagination. Now compared to on the ground, you'll notice here that we've got our RPM and it's stable now at 2,400 RPM. And we've got our manifold pressure, which is nice and high, indicating that we've got good engine power being produced. So we're nice and clear away from the airfield now, so what I'm going to do is I'm going to revert to this climb section here. So you'll notice it's 85 to 95 knots. Well, we're at 90, so we're happy with that. Throttle 23 inches or full if less than 23 inches. Well, we've got good weather conditions. 23 inches is the top of the green. So because of that, what we're going to do is we're going to have to adapt our climb attitude now, because we're producing less power. But you'll notice on the right hand side the RPM is still 2400, so the governor's doing its job and telling the aircraft, well actually this is what I want you to do with the engine. We're going for constant speed prop here. We've gone a bit fast so we can afford to raise the nose, retrim. But we're now establishing our climb at 23-24, so 23 inches of manifold pressure, 2400 RPM, exactly as the book says. Now you can then mess around with a mixture as well to get 15 gallons per hour, or rich if under 15 gallons per hour. Okay, so in terms of your fuel flow, you can see we've got 16 here. So what's your speed, attitude and direction whilst we're doing this? And you can use the mouse wheel on it as well at the moment, so what you can do is just tweak it out. It doesn't need much to change its gallons per hour, and that would be your climb setting now for quite some time. Cowl flaps are open because we're producing a lot of power and a lot of engine heat, and what you're trying to do is you're trying to manage the cylinder head temperature. We're going a little bit slow there because I'm clicking on various things rather than concentrating on flying. So we'll climb up to about 3,000 feet and then we'll have a quick look at that. So as I say, you've seen the significance of what happens with the RPM when we move the throttle in terms of its stability. Now, one of the things that we spoke about in the sort of middle bit, the sort of theoretical bit, for want of a better way of putting it, is that one of the things you can notice as well, as you climb, your manifold pressure will gradually drop away, so you can gradually add more throttle as you go, and that's because of the changing air density as you go up. But anyway, one of the things we mentioned was in relation to the RPM and manifold pressure and the balance between the two, and how the prop changes its profile, its positioning with the airflow in terms of that. So we're a little bit late, 3,000 feet, we'll level out there, we'll go into a cruise attitude. We'll leave the power B to accelerate for a bit. And what I'll probably do in a moment is I'll probably put it on autopilot so that we can then talk through the rest, the engine controls, without me having to faff around. Okay, so what are we at? 3,000 feet. But what I can do is I can put the autopilot on. And if I press my... I need to have a quick look. I need a pair of glasses for this sort of nonsense. If I press Alt now, it will hold the altitude that it's engaged at. So it's not a pre-select to the Alt. It just holds the altitude you're at. Okay. It says cruise 15 to 23 inches at 2,000 to 2,400 RPM. There's a couple of things we're going to discuss now. There is, we can afford to close our cowl flaps a bit now because we've got plenty of airflow coming through the engine. We will also lean our mixture off a little bit more. Okay. Bring the power back a little bit as well, just so we're not going to go massively off into the distance. Now, there's a couple of golden rules with this. There used to be a fallacy many years ago in terms of general aviation about a thing called over square. Now, over square basically in theory was where, ignore this for the moment, I'm going to come back to this in a bit, but over square was the theory that you should never have a higher manifold pressure, let's put it onto heading, you should never have a higher manifold pressure than RPM. So for example, you should never have 25 inches manifold pressure at 24 inches of RPM. Well, you can just see in the takeoff we've had to do that. But what you should be doing is following the instructions provided by the aircraft manufacturer. Now this is the bit where you have to go into the various tables that are produced by A2A or whichever manufacturer it is of whichever add-on, or even if going online, to find out the combinations. And the reason is we're going to want to try and perform a particular speed, and we're going to need to use a specific power and speed setting in order to do that. So for example, looking at my notes, at a pressure altitude of 2,000 feet or 4,000 feet, between the two, let's have a look at its speed. So 140, let's have a look at that, 136, let's go for 136 knots, true airspeed. So we're looking at 2300 RPM at 24 inches. Now what you're supposed to do in general practice is you're supposed to do what's called throttle back and rev up. So any changes going down should have the throttle reduced first and then the prop. Any changes going up should have the prop increased and then the throttle. Now if it's making small differences, so you're only varying it by a couple of inches manifold pressure, and it's within the range that's acceptable in terms of the designer's range, and that's fine. So we're looking for 23 at the minute, so 23 of each. We're already below 23 here, so what I'm going to do is I'm just going to pull the prop out until it comes out quite quickly as well, till we'll get to 2300. So a little bit more in. A little bit bouncy. I don't want it bouncy, I want it to be stable at 2300. And then what we can do is we can increase our throttle back to 2300 and we'll see what performance we get. So there's 23, and finally the good book says that at that we should have 13 gallons per hour. So now what we can do is we can lean our mixture off and go for 13 gallons per hour. And according to the book figures, that should give us about 136 knots, 135, 136 knots true airspeed. Okay, so true airspeed. Some will know what true airspeed is, some won't. So in terms of true airspeed, what we can do is we can just get our outside air temperature in degrees, 9 degrees C. Then we can go to our little nice TAS converter up here. If you'll excuse my screen nonsense, you can see up here we're at 4,000 feet and it's got the temperature across the top. So what we're going to do is we're going to move 4,000 feet till it gets to about +9, which is about there. And that tells us what our true airspeed is. So we're doing a little bit better than we'd anticipated. We've got 141 knots, I was expecting 138. So the chances are somewhere along this I've probably got it slightly out of skew, but it is still dependent on the air. I mean, even just moving this a little bit has a massive difference on what goes on there. Look, that's just one click. So if I'm one click out, all of a sudden it's null and void really. But there we go. So that's it in the cruise. Basically you read off your table and you just set the numbers. This is how fast your prop is turning, what the target is for the constant speed unit. This is your throttle setting, which is basically how much air and fuel you're throwing in, and then this is your fuel flow as per your mixture. Not your fuel, sorry. Your mixture affects your fuel flow, but what your mixture is actually affecting is the fuel-air ratio. So it does affect the fuel flow, because if you're saying I want lower proportion of what's going in the engine to be fuel, you'll have a lower fuel flow. So what we'll do is are we on heading? Yeah, let's just turn ourselves all the way around the other way. Go back towards Coventry. I was going to need to talk about the descent. Now, the engine can only produce full power at max RPM. So in the cruise what we're doing is we're basically saying we want the engine to be more chilled, more relaxed. We don't want it to thrape itself. Now in something like an A2A Cessna that becomes incredibly important, because if you thrape this engine it will bite you. It really will bite you. These things need to be treated just like the real thing. And if you start messing around and just flying everywhere at 2400 RPM, the wear that you're putting into your engine and prop system is quite significant. So it's worth bearing that in mind. Likewise, if you're going back into the climb, then obviously you need to consider what you're doing in terms of your throttle setting and your pitch. So we're at quite a good fuel-air mixture, so what we'll do is we'll turn around. Unfortunately, I don't have much of a... I haven't got a setting mapped for my my prop. I've only got one set for my throttle at the minute. This is Bruntingthorpe in the UK, by the way. It's not particularly well modelled here because this is FTX Global, but never mind, eh? Now, if I'm going to go into a climb from here, I can't just rock the throttles forwards for the climb. I'm going to put us back onto fully rich, but what I need to do is, if you remember, I said rev up and throttle back. So I've got to rev up and then I can increase my throttle and I can go to whatever it wants to be. So actually we're going to go for 23 inches, which is the recommended climb power setting. But you'll see now that we've got between 5 and 900 feet per minute rate of climb. So that's climbing. If you're descending for any particular length of time, you throttle back, and then as you change your pitch and sort yourself out to descend, what you would then do is you then reduce your revs accordingly. So as I say, to increase you rev up and then you use your throttle. If you're decreasing, you throttle back and then you rev down. So that's the basics of how to control that thing. Now what I would say is that when you're doing general aviation, general handling, or you're coming into land, or something where you might need very quick full power for your engine, always have that fully in. Always have it fully forwards, because realistically that's what you need. Now that's it in effect, really. That's the constant speed prop. The main aim of it is to enable you to have the best efficiency in terms of power, and using the most power available and transferring that into the air in the most efficient mechanisms possible. Couple more things to go through though. One of the things to go through really is the fact that, if you remember, I said that the governor sets the target RPM, but if the engine RPM is lower than the governor's limit, let me go through this a slightly different way. It's got 2400 RPM set. If I increase the power, the only way it can stop it going too far above 2400 RPM is to increase the bite that the blades take out the air, so to make the blades turn to a more coarse position, a greater angle. That extra drag keeps the RPM down. What it means, however, is you're taking bigger bites, and as you can see, you start to speed up, and you speed up quite quickly. If I take my power off, you can see that the needle, the tachometer, starts to try and drop, but the governor says, hang on a minute, I'm not going to let you do that, and it finds the blade off, finds the blades off on the propeller. What you then end up with is a situation where you slow down, and that's basically it. So if I push it forwards, the governor says no, you can't increase. I'll control the prop speed by taking bigger bites of the air. That slows the prop down, but it also produces more thrust, so you go faster. If I take the power off, the governor recognises that the prop's trying to slow down. It goes, I don't want you to do that, so it finds the blade off, so there's less air resistance on the blade, and at that point it then goes, you know what, you can go slower. So that's fundamentally all this is all about. That's Takeoff water over there, so we'll go over this way. That's fundamentally all this is about. Now, in terms of actual behaviour, we can look at the behaviour in terms of the needle and see how A2A have done. With any aviation, you should really try and avoid rapid changes of power and rapid changes of throttle, because it puts a lot of stress on the engine. So at the moment we've got quite cool cylinder head temperatures and EGT, so I'm not overly worried about it. But what I want you to do is watch the needle as I move the throttle rapidly. So as I move it, close it rapidly, you can see there's a big drop. The blades fine off, but it takes them a while to do it. And then it gets to the point where they can't fine off anymore. And now we're losing airspeed and we're losing RPM because the blades have gone to a fully fine position. And there's nothing that we can do to stop that from happening. Open it fully throttle, you'll see it overshoots, and then the governor stabilises. And it's because of this oil return system it uses. The oil system it uses with the piston in the hub, in the spinner, in the propeller hub, that has a slight delay in it, because if you imagine what's happening is it's going the wrong way around. What we're doing is we're saying to the engine, here's more fuel. Consequently, the engine tries to speed up, but there's a delay before the prop recognises the engine's speeding up, and it then has to increase the blade angle to prevent the blade speed from increasing. But obviously there's a delay in the system, so if I take it off you can see it drop, if I add it on you can see it rise. And that's one of the things, it can accept a momentary delay, but you can see if I really mishandle it, I can get it to go wild. Love the fact the prop sound changes as well, by the way. Okay, so that's one of the things to be aware of. The second thing is, as I said at the start, when you're on the ground, one of the things you've got to remember is that the engine might not actually be turning over fast enough to generate 2,400 RPM or whatever it is. So if I drop the power completely now, you can see that I can now control the speed of the prop by the speed of the aircraft. You see it increasing slightly, and if I pull back, you'll see the speed of the prop come down, just the same as on a single engine fixed pitch or even twin fixed pitch prop aircraft. So, okay. So descent power is acquired, mixture adjust, we're fine, we're fully rich. Cowl flaps will close at the moment. Don't need those. Altimeter barrier is set, fuel selectors to both, and wing flaps as required. We'll go to first stage flap at the minute, and we'll come back and land. Now, as I say, there's an awful lot to this, and one of the things you'll find is that if you use it correctly, you extend the range of this thing massively. But not only that, you'll extend the lifespan of things before they start to break. And in an aircraft such as this, where it's quite accurately modelled, that becomes quite important. So, landing checks. Well, airspeed 70 to 80, we're not there. We're going to join on an extended final. Wing flap as required, so we've got first stage flap at the moment, and we're going to look and come in for a landing. Now, one of the things you can see now is even though I've got my RPM set for 2400 because it's fully in, we're only at 2000, and that's because the engine isn't turning over fast enough for the governor to have any effect. It's quite a clever system. It's interesting to see how the gauges behave. The gauges do behave very similar to the real thing. I have to say though, as a caveat, it's an awfully long time since I've been in an aircraft where I've had anything other than a FADEC system. The last complex aircraft I had FADEC. It was a DA42 was the last piston complex engine I flew. We're only at an idle power setting to bring the altitude down nicely. Approach speed 70 to 80. Well, we're only just inside that, but we are high. We'll take full flap to help us get down, and possibly side slip a bit as well. What's our rate of descent? 1,000 feet a minute. I think we're going to need more than that, guys. I think we're going to need more than that. This is just a ham-fisted landing. There's no attempt here to actually do anything other than just bring it down in some sort of ham-fisted attempt at a landing. Try and maintain our 70 knots. The wind's kicking us around a little bit, which is not very nice. Rate of descent's building nicely though. Look at that. Got 70 knots. Nice. Now I don't reckon we're going to be too far from the glide slope any minute now. Need to get some power back on so that we land with power. The last thing you want to be doing is landing idle like a power off descent, because you've got very little control then over where you actually touch down. So the first red light's come in. I'm going to arrest the rate of descent because we've got downwards momentum at the minute. Get a bit of power back on. Now 3-degree glide slope, we're doing 70 knots, so we want about 350 feet a minute rate of descent to maintain 3-degree glide slope. Slightly left of centre line, coming back, correcting nicely. If anything, slightly fast, there we're going slightly too high again. A lot of people have made remarks as to how to land this thing. Treat it gently, try and get your speed right. To start with, it's always important to get speed right above anything else, and look into the distance. Look far into the distance as you can. What you're aiming to do is to make sure that what your viewpoint is as far into the distance as you can get. 3 reds now, but I'm not really particularly bothered because our touchdown point is fairly constant. Coming over the threshold, 70 knots, reducing to 60. Bring a bit of the power off. Try and actually maintain centerline, which would be nice. But I know a lot of people have a tendency to bounce this, and I'm not. Just put a bit of power back on. And I'm not averse to bouncing it occasionally myself, but there we go. Hopefully you guys found it useful in terms of constant speed props, what they do, how they work. So let's just get flaps up. Cowl flaps open. Because we're not at high power setting anymore, but we do want the air to get through to cool the engine down, and then securing the aircraft. So I'll leave you guys with that. I'm going to go and park up, shut down, and enjoy a cup of tea. In the meantime, please feel free to leave any comments in the comments section of the video. Likewise, if there's any professional flying instructors out there wish to add their thoughts, then please feel free. It is by no means an exhaustive or perfect discussion on the setup in terms of constant speed units. It's just intended to be something that can give a little bit more information to those who are in the flight sim community as to why they may or may not want to mess around with it. And it does add weight to the fact as to why I think the A2A Cessna is such a good aircraft, because the presentation of the effects of using it are so good. The book figures that you get, it's so close to them, it's scary. You know, it's almost as if they've gone through every single digit and every single number to achieve it. It's quite remarkable. But there we go. As I say, guys, I'm going to go and shut this down. I'm going to look after my aircraft, wipe it down, make sure it looks good and there's no flies stuck to it. In the meantime, if you enjoyed the video, please don't forget to tick like, share or subscribe. Your support is much appreciated, and it does help me with the channel in terms of getting the views and getting the support that makes it all worthwhile. So as I say, guys, don't forget to tick like, share or subscribe, and I shall speak to you soon. Take care.